Have you ever wondered what secrets lie beyond the Milky Way in the smaller galaxies that orbit it? These satellite galaxies are not just cosmic companions. They hold unique mysteries and fascinating insights into the universe's history and evolution. Did you know that some of these galaxies are newcomers, while others have been around for billions of years? Join us as we explore the 7 most intriguing properties of the Milky Way's satellite galaxies and uncover the hidden wonders of our cosmic neighborhood. The diversity of satellite galaxies. The Milky Way's satellite galaxies are a marvel of variety, each one with its own story to tell. Some, like the large and small Magellanic Clouds, are bold and bright, easy to spot even with the naked eye from certain parts of Earth. Others, such as the ultra-faint dwarfs, are barely detectable, their faint glow hiding some of the universe's most ancient secrets. This range in brightness, size, and structure is what makes these galaxies such an incredible subject of study. In some of these satellites, you'll find regions teeming with young, newly formed stars. For instance, the large Magellanic Cloud is rich with star-forming nebulae, where hot, massive stars shine brightly against swirling clouds of gas and dust. On the other hand, galaxies like the Sculptor or Bootes dwarfs are much quieter. These galaxies contain predominantly older stars, remnants from an era not long after the Big Bang, making them cosmic time capsules that offer a glimpse into the past. The way these satellite galaxies interact with the Milky Way is equally fascinating. Some, like the Sagittarius dwarf galaxy, are in the process of being consumed by our galaxy's gravity, leaving streams of stars in their wake as they are slowly pulled apart. Others, like the Magellanic Clouds, maintain a more stable orbit, though even they are subtly influenced by the gravitational forces of the Milky Way. These interactions not only shape the satellites but also contribute to the formation and evolution of the Milky Way itself. This diversity is more than just interesting, it's crucial for understanding the broader picture of galaxy formation and evolution. Each satellite galaxy is like a piece of a cosmic puzzle, revealing how galaxies merge, interact, and grow over billions of years. By studying their unique characteristics and behaviors, scientists can piece together the history of the universe, gaining insight into the forces that shape our galaxy and the cosmos beyond. Galactic cannibalism, the Milky Way's appetite. The Milky Way isn't just a majestic spiral galaxy, it's also a cosmic predator with a history of consuming smaller galaxies. This process, called galactic cannibalism, is how our galaxy grows and evolves over time. When smaller galaxies stray too close, the Milky Way's powerful gravity begins to pull them apart, gradually assimilating their stars, gas, and dark matter into its own structure. It might sound destructive, but this process is a key driver of galaxy formation and evolution. One of the most famous examples of this is the Sagittarius dwarf galaxy, which is currently being devoured by the Milky Way. Streams of stars from this galaxy, known as tidal tails, are now stretched out across the sky, forming a bridge of stellar material that wraps around our galaxy. These stars, originally part of the dwarf galaxy, are becoming part of the Milky Way's outer halo, blending seamlessly into its massive structure. But Sagittarius isn't the only galaxy to face this fate. Scientists have discovered that the Milky Way has absorbed numerous dwarf galaxies over billions of years. Some of these mergers happened so long ago that the evidence has been completely incorporated into the Milky Way, while others, like the Gaia-Enceladus merger, have left behind distinct populations of stars with unique compositions and motions. Each act of galactic cannibalism leaves subtle traces that astronomers can study to uncover the Milky Way's growth history. This process isn't unique to the Milky Way, it's a natural part of how galaxies evolve in the universe. As galaxies collide and merge, they create stunning displays of cosmic interaction, from starbursts to streams of gas and dark matter. For the Milky Way, this appetite for smaller galaxies has been essential to its development, helping it grow into the massive, dynamic structure we see today. By studying galactic cannibalism, we learn not only about the Milky Way's past but also about the dynamic forces shaping galaxies across the cosmos. Star formation and tidal interactions. The relationship between the Milky Way and its satellite galaxies isn't just a one-sided gravitational pull. It's a dynamic interaction that can spark some spectacular events. When the gravity of the Milky Way tugs on a smaller satellite galaxy, it creates tidal forces that can compress gas and dust within the satellite. This compression can ignite bursts of star formation, leading to new generations of stars lighting up the galaxy. It's like a cosmic trigger for stellar creation. A great example of this is the large Magellanic Cloud, one of the Milky Way's most prominent satellite galaxies. Its close gravitational interaction with the small Magellanic Cloud in the Milky Way has stirred up its internal gas, creating regions like the Tarantula Nebula. This nebula is a star-forming powerhouse, producing some of the most massive and luminous stars in the universe. These tidal interactions are responsible for transforming otherwise quiet galaxies into vibrant star-filled regions. The effects of tidal interactions aren't limited to the satellite galaxies themselves. The Milky Way also feels the impact as streams of gas and stars pulled from the smaller galaxies feed its outer regions. This influx of material can fuel star formation in the Milky Way, especially in its outer halo. These tidal streams act as bridges, connecting the satellite galaxies to their massive host while enriching both with fresh material for future generations of stars. These gravitational dances are more than just beautiful. They provide essential insights into how galaxies evolve and sustain themselves over billions of years. They show that even smaller galaxies play a significant role in shaping the larger cosmic structures around them. By studying these interactions, astronomers uncover the delicate balance of forces that drive star formation and maintain the dynamic nature of galaxies, like the Milky Way. The role of dark matter in satellite galaxies. Dark matter is one of the most mysterious and fundamental components of the universe, and it plays a crucial role in the existence and behavior of the Milky Way's satellite galaxies. These small galaxies are often surrounded by an invisible halo of dark matter that provides the gravitational glue holding them together. Without it, these galaxies, composed of relatively few stars and sparse gas, wouldn't have the gravitational strength to resist being torn apart by the Milky Way's immense pull. For example, studies of the Fornax and Sculptor dwarf galaxies reveal that their motions and structures only make sense when the presence of dark matter is factored in. By measuring the velocities of stars within these galaxies, astronomers have concluded that there's far more mass present than can be accounted for by visible matter alone. This unseen mass, dark matter, dominates their gravitational dynamics, acting as the unseen architect shaping their formation and survival. The influence of dark matter extends beyond holding satellite galaxies together. It also dictates how these smaller galaxies orbit the Milky Way. The vast dark matter halo enveloping our galaxy creates a kind of gravitational scaffolding that guides and stabilizes the orbits of satellite galaxies. This interaction between the Milky Way's dark matter halo and that of its satellites determines how they cluster, move, and even collide. These interactions give astronomers vital clues about the larger dark matter structure of our galaxy and the universe as a whole. Understanding the role of dark matter in satellite galaxies isn't just about solving cosmic puzzles. It's a way to test our models of the universe. By comparing the observed behaviors of these galaxies with simulations, researchers can refine their understanding of dark matter itself. The study of these small dim companions is unlocking profound insights into the nature of a substance that remains one of the greatest enigmas in modern astrophysics. It's a reminder that even the unseen has a massive impact on shaping the cosmos. Newly discovered satellite galaxies. The Milky Way's family of satellite galaxies is growing, thanks to advanced telescopes and innovative research methods. Over the last few years, astronomers have uncovered a surprising number of new satellite galaxies orbiting our own. These discoveries not only expand our galactic map, but also offer a wealth of insights into the dynamics of galaxy formation and evolution. Some of these newly found galaxies are so faint and compact that they were nearly invisible until now. One example is the discovery of ultra-faint dwarf galaxies, which are among the smallest and dimmest galaxies known. They contain just a handful of stars spread out across vast distances, making them difficult to detect. However, instruments like the Dark Energy Camera and data from the Gaia mission have made it possible to spot these elusive objects. These faint galaxies are not only fascinating in their own right, but also help scientists explore the limits of galaxy formation in the universe. Some of the new satellite galaxies have peculiar orbits or unusual properties that set them apart from others. For instance, the Antlia 2 galaxy, discovered in 2019, is enormous in size yet incredibly faint. So faint that it was dubbed the ghost of the Milky Way. Its discovery raised intriguing questions about how galaxies can form and survive in such extreme conditions. Each new find, whether it's a faint dwarf or a massive but hidden structure, challenges what we thought we knew about the cosmos. These discoveries are more than just cataloging new objects. They give astronomers a closer look at the Milky Way's past interactions and provide essential data for understanding the role of dark matter, the formation of galactic halos, and the impact of gravitational forces on galaxy survival. The ongoing search for new satellite galaxies is like assembling a cosmic puzzle, where each new discovery adds a piece to the grand picture of how the Milky Way and its companions came to be. The unique histories of satellite galaxies. Satellite galaxies orbiting the Milky Way are not just passive companions, they carry unique stories of their origins and transformations. Each satellite galaxy has a history shaped by countless interactions with larger galaxies, the pull of gravity, and the dynamics of their own stars and dark matter. These smaller galaxies, despite their size, can reveal astonishing details about the evolution of the cosmos and the Milky Way itself. Some satellite galaxies were once thriving and independent systems before being captured by the Milky Way's gravity. Over billions of years, their orbits have often brought them dangerously close to our galaxy, stripping them of stars, gas, and dark matter. This gravitational interaction called tidal stripping has left some of them almost entirely bare, reduced to sparse collections of stars barely clinging together. These remnants are like ancient ruins, offering clues about the destructive power of galactic interactions. A fascinating part of their histories involves the stars they carry. Many satellite galaxies show evidence of multiple generations of star formation, with some containing stars that are among the oldest in the universe. By studying these ancient stars, astronomers can piece together events that occurred shortly after the Big Bang. Some of these galaxies, like the Sagittarius dwarf galaxy, even show traces of having merged with other smaller systems before becoming satellites of the Milky Way. These interactions create a tapestry of histories that reflect the chaotic processes of galaxy formation. What makes these histories even more compelling is the role of external influences. Some satellite galaxies have experienced bursts of star formation triggered by interactions with the Milky Way's halo, while others have had their growth stunted by the lack of gas due to environmental factors. Each satellite galaxy represents a different chapter in the story of cosmic evolution, giving us a window into the processes that have shaped galaxies across the universe. Their unique paths remind us that even in the vastness of space, every object carries a story worth exploring. The future of the Milky Way's satellite galaxies. The Milky Way's satellite galaxies aren't static entities, they're part of a cosmic dance that continues to evolve. Over the coming billions of years, the gravitational interplay between these smaller galaxies and the Milky Way will shape their futures in ways we're only beginning to understand. Some will survive as companions, while others may be torn apart, merging their stars and materials with the larger galaxy. Many of these satellite galaxies are gradually spiraling inward due to the immense gravitational pull of the Milky Way. This process will eventually lead to their disruption and absorption, a phenomenon known as galactic cannibalism. As they approach the Milky Way's core, tidal forces will strip away their stars, gas, and even dark matter, scattering these materials throughout the larger galaxy. The Sagittarius dwarf galaxy is a perfect example of this, as its remnants are currently merging with the Milky Way, leaving a stellar stream in its wake. Other satellites may remain relatively intact, orbiting the Milky Way for billions of years to come. The large and small Magellanic Clouds, the most prominent of these satellite galaxies, are expected to collide with the Milky Way in the distant future. Their interaction is likely to trigger bursts of star formation, revitalizing regions of our galaxy and adding new stars to its already sprawling population. Such collisions will also help scientists refine models of galaxy evolution by providing real-time examples of these transformative events. As technology advances, future telescopes and space missions will provide clearer insights into these satellites' trajectories and ultimate fates. These discoveries won't just reveal the destinies of these smaller galaxies, but also offer clues about the long-term future of the Milky Way itself. The story of our galaxy is intricately tied to the lives of its satellites, and studying their futures helps us understand the larger picture of cosmic evolution. Their dynamic interactions remind us that the universe is far from a quiet place. It's a constantly changing, interconnected web of matter, energy, and motion. That concludes our cosmic journey through the Milky Way's satellite galaxies, from their fascinating diversity to their dynamic past and intriguing future. These tiny companions hold the keys to unlocking the mysteries of galaxy formation, evolution, and the nature of the universe itself. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the wonders of the cosmos with us.